Hello again, I will explain task 4 and task 5 of hydrodynamics course. Task 4 is talking about hydrostatic pressure determination. In the beginning I want to define what is pressure. Pressure is a force divided by the surface. So is pressure in Pascal equal force in Newton over the surface area by square of meter or meter square. The official pressure unit is Pascal. It is a very small unit. 1 Pascal equal 1 Newton over square meter. We have some of conversion for units, like from bar to Pascal, from atmospheric pressure to Pascal. In the ABI standard unit, PSI is the standard one. So the main concept is that hydrostatic pressure is equal to rho times G times H, where rho is the density, fluid density. G is the gravitational acceleration. It is a constant 9.8. H is the vertical height of the fluid. So at depth D, the pressure exerted by a column of fluid is the same for all hole configurations, whatever the shape of the hole. It will relate it to the height of the column of the fluid. And also for the fluid specific gravity. Hydrostatic pressure is the pressure exerted by the weight of a static column of fluid, which is function of height and fluid density. The YouTube effect, not YouTube site, the geometry and the dimensions of the fluid column have no effect on hydrostatic pressure. If the mud weight in the pipes and annulus are different, a YouTube effect occurs due to the difference of pH hydrostatic pressure as the system seeks equilibrium. So the slug of weighted mud pump just prior to a trip takes advantage of this effect to keep the inside of the pipe dry at drill floor level. So the mud weight has a very important mission to force the fluid inside the formation and don't have a kick or don't have a loss. So to define this displacement volume, like in this pipe and annulus, we can find that the first one is at certain depth, so they have the same pressure, so they have the same level. While in the second one, the mud weight is have the air gap height above the weighted mud, and it is forced the fluid beneath it to raise up in the annulus. How to define this in loads? Number 1, slug height equals slug volume over pipe interval volume. Air gap height equal the slug height times slug density minus mud weight over mud weight. So the displacement volume equal air gap times pipe interval volume. That will by this way you can calculate the displacement volume in the annulus. Okay, our problem consists of 3 parts. The first part is convert the following values to the requested units, and it is simple. Number 2 is for the following data. What is the length of the air gap created by the slug? You can find that it is a direct problem by using the previous described laws. Number 3, in the Gulf of Suez area in Egypt, a well drilled in an exploration field with fresh mud and it's equal to 12 pound per gal. The hydrostatic pressure can get from this formula. It is required to calculate the hydrostatic pressure in range of depths from 2000 to 2 and 200 meter with 10 meter depth interval. Note the bulk density equal 1 gram over cc. Number 2, construct the relationship between depth and hydrostatic pressure. Number 3, explains the resulted relationship. Okay, simple. You can calculate the hydrostatic pressure by using this formula. You will change the height, which related to the depth here, and started from 2000, and you will finish at 2200 by interval of 10 meters, and the rho will be constant 1, and 0.435 is important to get hydrostatic pressure in PSI. It is so simple. Okay, now we will go to task 5. Task 5 is related to the real-time indicators of overpressure zones. Number 1, the analysis of drilled cuttings, shale density. The cutting density can be monitored to detect the onset of transitional pressure increases through shale or clay intervals. With depth, shale density shows a normally increasing trend due to increased compaction and reduced porosity and fluid volume in comparison to the matrix content. Okay, so to explain what we want to say in this point, you need to imagine that we have a normal trend for shale density or for cuttings density. As the depth increase, so compaction will increase, and logically density will increase. But in the overpressure zone, it is a zone, maybe shale, but still confined and have a certain amount of fluid, and this certain amount of fluid is confined. So this zone will be overpressured, but the density of the shale cuttings will be lower than the normal trend. So we will see a transitional zone and overpressure zone, which may be lower than that normal trend. Okay, to continue, through a transitional zone, as pressure gradually increases, the compaction rate decreases, and shale density will show a corresponding gradual decrease to the normal trend. Through the overpressure zone, which with constant pressure and compaction rate, the shale density will typically show a trend equivalent to the normal compaction trend, just offset to reflect the pressure differential. Okay, a cutting drilled near balanced conditions will be larger and more angular in shape than one which is drilled under conditions of greater overbalance. It will be more thinner, more sharper. Okay. Now, to go to the problem number 5, we have the rule to get the pore pressure. Okay, this method called Griffin's and Bullard method. The pore pressure equal H minus 0.535 times ds, where the ds is the depth of sealing that makes this that confines the fluid inside the overpressure zone. Okay, where H is the depth of the overpressure zone, or in the pressure in the overpressure zone. Okay, by applying this rule, we can find that the output will be like that. Okay, wait. Okay, now screen pointer pin. Okay, by drawing the relationship between density and depth. Okay, density equal x-axis, depth per feet, and density per gram cc. We can find that this the log signature in this reservoir or in this overpressure zone will be like that. This is the normal trend and suddenly changed. Okay, if we get the normal trend of the reversed part, we can find the ds, depth of sealing, and this will be the first point of overpressure zone, and the second one, the third one, and so on. So ds in this example will equal to 13,000 feet. Okay, now we can take this part to. Okay, now we can get this part to calculate pore pressure by using H minus 0.535 times ds, where ds is 13,000. Thank you.